So for homework, please do examples 4.33 and 4.34 because the grunt work part, in fact, try to set up the problem itself and then get through the grunt work. Is quite a bit of grunt work in there, but it actually gets worse sometimes for this type of problems. And doing grunt work is good for building character. Okay, I mean, I did my share of grunt work in my day, and look at how good I turned out, right? So next, let's look at example 4.35, which is on page 445, maximizing revenue. That's what businesses always love to do. To let's see, we have a car company, okay, that charge a price of P dollars, so P is the price, to rent some car. The P has the range of 50 to 200 in the sense that when P is 50, all the cars are rented. That is the price of $50. All the cars are rented. And when P is 200, they can't rent any, okay? Because nobody's such a sucker to pay that much for the car. So they're trying to figure out if there is a price just right that they can rent it out so that they can have the maximum amount of earnings. Now, so this relationship is this that they found out is in this situation, the 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 number of cars in terms of price of the car is equal to 1,000 minus 5p. And when you plug p equals to 50, that's 750 cars, which is all the cars they rented. And when p is, what was it, 200, right? 1,000, I'm missing a zero here. Okay, so when p is 200, of course, this whole thing goes to zero. And thus, so p goes from, for this equation, we only care for p that's bigger than 50 and less than 200. Any more or less than that is irrelevant to us, okay? So so let's consider this. Then of course the revenue, which we will call R is equal R, which is in terms of P, is equal to the number of cars times the price itself, which means it equals to 1,000 minus 5p. That's the number of cars times the price itself times p, which happens to be a fairly straightforward equation of so that will be 1000p minus 5p squared. Now as you can see, that's an upside down parabola, okay, of degree 2, which means it has a maximum point, and we're going to calculate that maximum point to figure out the nice price. So the derivative, which in this case happened to be very simple, so I'm gonna do it. I'll pick the easy one to beat up, right? So then that's 1,000, okay, and then minus 10p, which means, and if we set that equal to 0, that would mean that p equals to 100. So which means the price when you set it at $100 would give you the maximum profit of whatever. Okay, did they even ask what the maximum profit is? No, they did not. I guess not. Maybe they did not. I don't know. What? Okay, how much should they charge to maximize the revenue? That's what the question asks. So $100 a day, and that should do it. They didn't ask what the maximum revenue is, so we're not going to wear ourselves out doing that. So let's look at the next example, which is example 4.36. Now you have to, when you do this kind of problem, it has to make sense. Okay, if your answer is like 10,000, something is off. It's not going to make sense. But 100 sounds about right. So because remember p is between 50 and 200, so your answer seems reasonable, and you can accept it. Example 4.36, which is okay. Let's look at example 4.36, which is on the following page. Where we have an ellipse. Ellipse is represented by a formula that looks like this. Here is a standard ellipse plus y squared equal to 1. Ellipses are covered in pre-calculus or something, but if you don't remember much of it, it doesn't matter. The point is that's an ellipse, okay? And if you were to plot it out in the Desmos computer graphics calculator, then you come up with some ellipse of yours. Okay, so the question is, there's a rectangle to be inscribed in the ellipse, and what dimensions of the rectangle should have maximized the area. So let's draw our ellipse here. Ellipse is a flattened circle, sort of. They should be symmetrical, but I'll just let it be that way. And inscribed means the points of the rectangle are on the ellipse. Okay, here's my rectangle. Again, this should be symmetrical. My drawing is a bit off, but bear in mind, well, look at the drawing in your book. Okay, so then when we have a point of x, y, and we'll take, which is on the ellipse, where such that the rectangle, this distance is x, okay, and this distance is y. Okay, this is also x, and this is also y. Just the distance. So so we have a point on there, and for our example, for our problem, we only need to consider when x is bigger than 0. And of course, y is bigger than 0. Because when x goes over here, we're talking about this point, which is the same as that point, because they're symmetrical. So there's no point in even thinking about what happens when x is negative 0. Then the other x is bigger than 0, see? So we need to maximize some area. What is the area? The area is, of course, for the rectangle, is length times width. All right. Now, let me get my notebook. Now, when I prepared this problem, I did it differently than the way the book did, because I did implicit differentiation. So I will show you what I did, and I will talk about it from my way. I think my way is maybe slightly shorter than what the book did, because implicit differentiation is sometimes easier, as we have done. So I will follow my way, but you can do it either way, of course. So let's go about my way. First, we are trying to find the area in order to maximize it. The area of the rectangle is, of course, length times width, which in this case is 2x times 2y, which is equal to 4xy. All right, so what do we need? Well, we need to figure out, to find the maximization, we need to take the derivative and set it to 0. So dA by dx, x is what we're going to take the derivative with, is if we do the implicit differentiation, that would be 4x, first term times derivative of the second, y prime, plus second term times derivative of the first, which is just 4. So far, so good. But then we also need to figure out what is y prime, right? So we'll take the implicit differentiation of this thing. So then take the derivative of this whole thing across by with respect to x. Now, if you do that, you get, so then we have 2x, okay, from here, 2x right down up here, divide by 4, taking the derivative, plus 2y, y prime is dy by dx, equal to 0. Okay, then we have, so we're trying to figure out what y prime is. Therefore, y prime equals to, all right, so y prime equals to, y prime here, we might have minus x over 2, and then have 2y, right? Which equals to minus x over 4y. That's right. See? And then, so we plug y prime in here, which gets, so that equals to, we are going to set the derivative to 0 in order to find the maximum point. So then we have 4x y prime, which is that thing, minus x over 4y plus 4y squared, because I'm going to stick another y down here. What? Okay. At this point, this part is canceled out. Okay, so that's good. Which we will set this to 0, and that will equal to, in other words, y squared. When you settle this thing, then you get y squared, then equal to slap that one to the other side is x squared. Okay, divide by 4. Yep, so far so good. See? So next, that's if you set it to 0. Now then we plug in this equation. What is y squared? Y squared is this stuff. There's the relationship of x and y. So then and plug it in here, we get y squared equals to x squared minus 4. So plug it in here, we get so x squared over 4 plus y squared, which is also x squared over 4, equal to 1. So that gives you x squared equal to 2. Okay, and which means x equal to square root of 2. All right, that's about it. And then the area is something. Did they ask for the area? What were they asking for? What should be the dimensions be? And what is the maximum area? Okay, so y equals to, from this equation here, we know that y equals to x over 2. Okay, and then so y equal to square root of 2 over 2. And then the area is 4xy, as we determined earlier. So the area is 4 times square root of 2, then square root of 2 over 2, and when that's all settled, that equals to 4. And that seems to be slightly faster than what your book did. Well, at least you don't have to deal with radical signs. But to know for sure, you're going to have to do it, because what the book did might also be fairly simple. Well, anyway, that's what I did, and I want to show you. So next, let's go to the next problem. Nope, there's more stuff on the other side. So my way is probably faster. Don't know. And let's look at the next example on page 449 after I erase the board. Example 4.37 is fairly straightforward, calculating some surface area of some box. So I will assign that as homework for you. It's not really much worth discussing for me to spend time. Therefore, for homework then, the problems that you need to do is on page 451. 315, 17, 19, 23, 27, 29, 33, 35, 39, 41, 45, 47, 49, 53, and 55. And note that the answer at the back of number 55, 355, is actually wrong. This is the first time I see a wrong answer in this book. But it's most definitely wrong. And if you look at the answer, you'll know why I say that. So bear in mind when you do problem 355. And now please go do your homework, and when you're done, come back to this video at this point, and I will explain some of the problems that I have starred in the assignment. All right, now that you are done with homework, let's look at some of the problems that I intend to do. First, I want to do 323. Number 323 is one of the earliest problems that you are assigned. I mean, in the series, but in the in the problem section. But it's actually quite tough. Okay, it has the letter T in front of the problem, which means well, you're going to find out what that means in a second. the question itself is innocent enough, okay? You're moving into a new apartment and notice that there's a corner where the hallway narrows from 8 feet to 6 feet. All right. What is the length of the longest item that can be carried horizontally around the corner? Now, how cute is that? So let's look at this problem. I will draw the corner here, something like that. And you have an object. Oops, it's not touching. Let's make sure it touches. Okay, you have, and whereas this is 6, okay, and then this is 8. Which is fine, but think about this. What does that mean? That means what happens is that you have, I'll draw another. What happens is that you're carrying a long piece of, let's say, I don't know, stick, okay, that you need. The stick over here in this hallway, the stick can be very long, right? It doesn't matter how long it is. You can, as long as the hallway is, you can carry the stick along, no problem. The question is when you get to the turning point. Once you get to the turning point, if your stick is long, you look like something like this, right? And you're like, uh-oh, it's stuck and it's not going any further, and you know it. So what do you do at this point? What you do is you're gonna cut off part of your furniture, the stick, whatever it is. You cut off part of your stick, then it will be able to move a little farther, right? And you continue cutting it off until some point where you have cut off a sufficient amount of your stick so that it can go around the corner. And then once it get past that, then you can let your stick grow again. Then or maybe I should say your stick is shrinkable. Yeah, let's cut it, okay? But once you get past that point, then your stick can grow again. Okay, let your stick grow. Once you pass that point, see, the stick can be long again, no problem, right? So the stick start out being long, right? And then gradually get shorter and shorter until you reach some shortest point. That's what we're looking for. So when the question asks you, what is the longest it can be, is actually asking you what is the shortest. You have to cut your stick to get around this thing. So the question asks you what is the maximum, but actually what you have to do is what is the minimum. Okay, that is, we're going to calculate the length of the stick until it reaches the minimum and find out what the minimum is to get through it. So having said that, let's draw a better picture. So that's the first picture. Now let's draw a better picture of your stick around that corner of yours. Okay, we'll draw the stick. You know that it'll look something like this, okay, where this length is 6 and this length is 8, and this thing drops down to be, and these two values, which I will call, this value I will call x, and this value I will call a. All right, and okay, let me show you what I did in case I forget to do so later. Then you can refer to it later if necessary. All right, so then well, x and a is something that we need to determine. Once we determine x and a, then we know what angle or how far or whatever it is that we need to turn this thing. What was the question again? The question says, where's my question? What is the length of the longest item? Okay, so we don't need x and a in itself. We just need to find out what is this length, right? And once you figure out x and a, then we'll figure out the length by, well, good old Pythagoras theorem of the hypotenuse. All right, so this length is also a, that distance, and that one is also x, and that matters. Now the next question is, what is the relationship here? We'll call this whole thing S, okay? S is what we're trying to maximize. Now, to do that, we have to first come up with a mathematical relationship. What is our relationship? Well, the relationship is between x and a and s and 8 and 6. You need to, well, at first that might not be that obvious, but if you stare at this thing more carefully, you notice these two triangles are similar triangles because these lines are parallel and stuff, okay? So these are similar triangles, and similar triangles has that rule of their sides being proportional. To be exact, what I mean is that that's the bottom of this triangle. A over the bigger triangle's bottom, okay, A divided by 8 is going to be equal to 6 divided by x. That's one of the rules of similar triangles. Their sides are proportional. So having said that, that's the first relationship we have. And the second relationship we must remember, of course, that's easier, is the Pythagoras theorem. S, what is S? Or to be exact, S squared equal the third side's a squared plus b squared. And so a squared is 8 plus a squared, and then b squared is 6. What? Okay, right. 6 plus x squared. X squared. All right, so that's that. And from this thing, we know that, what did I have? 6 divided by 8. No, I wrote something down wrong. 6 divided by x, sorry. Oops. Okay, see, 6 divided by x, that's the vertical wall. All right, so then the relationship here means that a equals to some representation 6 times 8. Okay, a equals to 48 divided by x. That's the relationship. And as by now you can see where this is going. We're going to plug a in here. Okay, so we have a relationship between s and x, and then we'll take the derivative, set it to 0, and come up with something, right? That is a noble ambition. That excuse me. What is wrong with this thing? Okay, some item started making noise. Anyway, so now that is our ambition, is to take the derivative and all that stuff. So let's do that. So next we will continue to have s squared equals to that thing, which is a is 6 over x. We'll write that down. 8 plus 6 over x squared plus 6 plus x squared. Now that looks fairly innocent, right? But when I went to do it, it didn't become so innocent. The derivative of this thing, even when I take the derivative with respect to the implicit differentiation, it ended up being a giant pain. Here's what I came up with. Look at the last line, okay? It became a polynomial to a fourth degree polynomial, which I can't begin to solve by hand. So what I did is went to some place called the root calculator. I found the root calculator and found out the root. And root turns out to be where x end up being this. Okay, I solved for x by the root and found some root that makes sense. There was also a negative root. Of course, that's not going to work. Or something like that. Anyway, at least I think I did. So the root I came up with is x equal to 7.268. And then s, if you plug all that in, then s equals to 19.731. Okay, after much struggling. So then that would be the maximum length that you can go around the corner, even though it's actually a minimum. I also plotted typed this graph into the demos graphics calculator, and it was able to also identify, and I recognize on there, just by the look of it, that this is its minimum point. And that would be the answer. So yeah. So next, what am I supposed to do next? Next, we will do problem 327. All right. 327 is a very, very interesting problem. Let's go look at it. That you have already done, right? But I will talk about it. The 327 says that the description is a little bit before the problem. It says you have a circular pool. Okay, fine. There are pools that are circular. That that has diameter is 40 meters, which is okay. So that's 40, and which means the radius is 20. So we'll write down there. There's your pool, and a lifeguard at the circular pool. So the lifeguard is over here on one side, and then what's happening? He has to reach some guy who's drowning on the exact opposite side of the pool. So some guy is drowning here. Okay, I'll put an exclamation point to indicate that something serious is going on. And then the lifeguard. Now we know that the lifeguard swims with a speed v and runs at a speed of 3v without knowing what v is. Okay, so what's the question? We need to, the lifeguard is going to swim like this. Okay, here's the angle theta. The lifeguard is going to do this. He's going to swim over there and jump out of the water and then run this way. Why? Because that will be the find a function that measures the total amount of time it takes to reach the drowning person as an angle of theta. And then you can figure out what is the fastest way to reach the drowning guy. So as the guy is drowning, we will sit down and do calculus. Okay, let's make sure the lifeguard get there the fastest possible. All right, which you have already done, but I will go over it. Well, in reality, what you do, this problem is theoretical. That is, you might calculate this one, and then during lifeguard training, you can tell them to, if that were to happen, you might want to swim a little bit to the side and jump out of the water. It's faster. But anyway, so here's what we are doing right now. Okay, so I came up with the answer. I will show you my notes here for a second, in case I don't remember to do it later. Okay, that should do it. And then let's talk about it. Now, to solve this problem, we are going to do this. Drawing this line. And then what is the angle here? Because this is radius and that's also radius, this is an isosceles triangle, so this is also theta. And which means this is 2 theta. And that's from, I don't know, geometry or something. Anyway, so that's that. And then next, we need to figure out we need to figure out 2 things, okay? First, we need to figure out what is this distance, right? And then we need to figure out what is this distance. Now, this distance right here is, by definition or something, of the radian, the sector is by definition of the radian is the angle times the radius. So this length is 20 of the radius times 2 theta. That's the length, okay, of this part, going from here to here. All right, and then this length here is more complicated because, well, we know what these 2 sides is, and then we know what this angle is. This angle is 180 minus 2 theta. So that's 20, and that's 20. And then we're going to use something called, I don't remember what it's called. Is the law of cosine, maybe? Yeah, whatever. Is the rule that says when you have a triangle, okay, that looks like this, where you have A, B, C, and here's an angle the small c. Okay, that's big C and that's small c. Small c is the angle, big C is the side. So the law of cosine, I believe, says that c squared equals to a squared plus b squared minus 2a. Where's my 2? Minus 2ab cosine c. That's the good old law of cosine. So C is symmetrical. It's similar to the Pythagoras theorem, except you have to do some subtraction here. So to plug that in, then our distance, that is that the lifeguard has to swim, he has to swim up here and then down here. So we add up these two signs. So the distance equal to, I'll call D for distance, equal to the square root of that thing. Let's plug it all in because that's c squared. So I'll take the square root of a squared is 20. B squared is also 20 minus 2 times a times b. They're both 20. I'm missing something here. Okay, they're both 20 times 20. 2ab cosine of the angle is pi over theta. Pi is 180 degrees. I mean pi minus 2 theta. Okay, that angle right here. So that is the straight stretch. And then plus the 40 theta, the 20 times 2 theta here, which is that part. 40 theta over here. All right. So, and then we have to, now we are stuck with a bit of a grunt work, but it actually comes out pretty neat. So I'm going to finish doing this. So D equals to, you have 20 squared, 20 squared, and 20 squared all the way through. Okay, so I'm going to take it out. So we have 20 squared here. And then we keep it a little simpler. That's 2 minus 2 cosine of pi minus 22 theta, sorry, in parentheses, and then plus 40 theta. Okay. That next, what we're going to do is, let me see, what else do I want to say? What I want to say is, we'll take this part, okay? So we need to figure out which part I want to talk about. Give me a second. I forgot to mention that this is problem 327, or write it down. All right, so now we are going to do some, what is that? Trigonometric identities. The identity says that this is the cosine of sum of angles, difference, whatever. So the cosine of sum of two angles, cosine of a plus b, equals to, look that up in your your trick book, right? Trigonometry book. It equals to cosine A cosine B minus sine A sine B. And therefore, the cosine of pi minus 2 theta equals to, plugging in pi as A and negative 2 theta as B, then you guess like cosine pi is 0. Now, cosine pi is minus 1. Okay, so it becomes minus cosine minus 2 theta. Cosine of minus 2 theta is just cosine 2 theta, because cosine's negative degrees are the same. Let's see, what else do I have? And that's about it, because sine of pi is 0. So this is the entire answer. So we can plug this equation in here, and then we have d equals to 20. And this time we'll factor out the square root of 2 in here, so that we have 1 minus, what does it become? Does it become plus?